Hey everyone, and welcome. Today we're going to tackle a big one, a 14-mark GCSE Physics question. Now, I know these massive questions can feel a bit scary, but honestly, they're really just a bunch of smaller puzzles strung together. So in this explainer, we're going to break it all down, piece by piece, so you've got the skills and the confidence to bag every single one of those marks.
Okay, let's dive right in. What you're looking at here is a classic experiment for investigating acceleration. You've got a trolley on a runway, and it's being pulled along by a hanging mass. Now, the really important bits are the light gate and the data logger. That's what's going to measure the trolley's motion with some real precision. Getting your head around this setup is, well, it's the foundation for the entire question.
So here's our game plan. We're going to kick things off by making sure we've nailed the experimental setup. Then, we'll get into the meaty part, turning the data into a graph and figuring out what it all means. And we'll wrap it up with a really important calculation. Let's just take it one section at a time.
All right, section 1, setting up the experiment. Getting these fundamentals right is so important for collecting good, reliable data. And let's be honest, these first few questions are a fantastic chance to pick up some pretty straightforward marks.
Okay, first puzzle. The trolley starts rolling down the ramp all by itself, even without the hanging mass pulling it. So what does that tell us? It means the slope's too steep. There's an unwanted force, a little bit of gravity pulling it downhill, and that's messing with our experiment. So how do we fix it?
And here's the beautifully simple solution. By moving that wooden block to the left, we lower the ramp, which makes the slope less steep. The idea is to find that perfect sweet spot where the trolley just stays put on its own. This is actually a technique called friction compensation, and it makes sure that the only force making the trolley accelerate is the one we want to measure, the pull from that mass holder.
On to the next practical problem. Just look at how that string is going over the sharp edge of the bench. You can almost feel it rubbing, can't you? Well, that rubbing creates friction, which is another one of those annoying, unwanted forces that's going to throw off our results. So what can we do to get rid of it?
And the solution is a simple but absolutely vital piece of kit: a pulley. By letting the string run smoothly over a pulley, we can change the direction of the force with almost no friction. This is so important for getting accurate results. It makes sure that the F in our F equals ma equation is as close as possible to just the weight of those hanging masses.
Okay, here we go. The most mark-heavy part of the entire question. For 4 big marks, we need to turn a table of raw numbers into a graph. This is such a fundamental skill in science, right? It's about turning that data into a visual story that really shows you the physics at play.
So here's our mission. We've got a table of results on the left, showing how acceleration changes with the resultant force, and we've got a blank graph on the right. Let's get inside the examiner's head and break down exactly what they're looking for to give us full marks.
Now, the good news is the question itself is basically giving us a to-do list, 3 crystal clear instructions. We need to choose a scale, plot the points, and then draw a line of best fit. Let's just walk through each one step by step to make sure we get all 4 of those marks.
First things first, the scale. Let's look at our numbers. Our force values go up to 0.25 newtons. The absolute key here is to choose a linear scale. That means each box has to represent the same value, and it needs to use at least half of the available x-axis. So a scale going up to, say, 0.30 or maybe 0.35 would work perfectly.
Okay, next up, we carefully plot each pair of values. For example, that first point is at 0.5 newtons on the x-axis and 0.08 meters per second squared on the y-axis. We're going to use a small, neat cross for each point and make sure we're placing them as accurately as we possibly can.
And finally, the line of best fit. Now, the physics tells us that force and acceleration should be directly proportional. And what that means for our graph is that our line must be a straight line and it must pass through the origin. That's the 0, 0 point. So grab a ruler and aim for a line that has roughly the same number of data points on either side of it.
Fantastic. So our graph is complete, but it's way more than just a picture, right? It's a really powerful tool that we can now use to describe the physics that's going on and even suggest ways we could make the experiment better.
Now pay really close attention to the command word here, describe. This is an exam classic. The question isn't asking why something is happening, it's just asking us to say what the graph is showing us. So what's the mathematical relationship that our beautiful straight line graph is telling us?
Because our graph is a straight line that goes straight through the origin, it shows a relationship of direct proportionality. Now, what does that actually mean in simple terms? It just means that if you double the force, you're going to double the acceleration. They go up together at the exact same constant rate. Simple as that.
Ah, a classic experimental improvement question. Here's a top tip for you. Whenever you see a question asking how to reduce the effect of random errors, the very first word that should pop into your head is repeat.
And here it is, straight from the horse's mouth. This is exactly what the mark scheme is looking for. To get both marks, you can't just say repeat the experiment. You have to be more specific. You need to say that you would repeat the readings for each force, and then, and this is the absolutely crucial part, you'd calculate a mean or an average, and you'd make sure to ignore any weird anomalous results.
Okay, we're on the home stretch. On to our final section, the calculation. This is where we step away from the graph for a minute and go back to the core theory, applying one of the most important equations in all of physics.
First up, a nice, straightforward recall question. This is a 1-mark gimme. We just need to write down one of the most famous equations in science. You probably know it as Newton's second law.
And there it is. Resultant force equals mass times acceleration, or F equals ma. You've got to burn this one into your brain because it's the tool we're going to need for this final 4-mark calculation.
All right, the final boss, a 4-mark calculation. Now, to get every single mark, you have to show you're working. First, write down the formula. F equals ma. Easy. Second, substitute the numbers the question gives you. 0.375 for the force, 0.6 for the mass. Third, you've got to rearrange the formula to find acceleration, so A equals F divided by m. Then you do the calculation. Finally, and so many people forget this, you have to round your answer to the number of significant figures the question asks for.
And this last step is just so important. Your calculator will probably spit out 0.625. But the question specifically asks for 2 significant figures. So the first significant figure is the 6, the second is the 2. To round it, we look at the third digit. It's a 5, and the rule is if it's 5 or more, you round up. So that 2 becomes a 3, and our final full-mark answer is 0.63.
And there you have it. We've totally broken down and mastered this question. But you know, a great scientist is never really finished. They're always thinking about what's next. We dealt with friction from the ramp and the string, but what about other sneaky sources of error, like air resistance, or maybe even friction inside the trolley's wheels? Asking these kinds of questions is how you design even better experiments next time.